Hello, everybody. Thanks for joining us. Today we're going to present the winners of the AVEVA Partner Games.
Welcome to our presentation for the AVEVA Partner Games. It's a really exciting time for us as we stand on the frontier of digital transformation, harnessing the power of advanced technology to drive sustainability in everything we do. We are the team It Is Obtainable to Be Sustainable. Our sector was around power, how best to utilize operational wind farms and cut down on unnecessary maintenance costs, driving that key idea of not only having profitable assets, but keeping them operational for longer, promoting long-term sustainability of wind sites. Our customer, Green Energy Wind, is spending too much time and money on maintenance for their wind farms. It's becoming quite clear that they are overspending on their budget, which has resulted in having to sacrifice purchasing equipment for commissioning new sites and cascading into poor operational efficiency and supplying power unnecessarily to wind turbines during repair windows. The main pain points that we've identified as part of their business case is that there's no single source of truth, there's unnecessary resource wastage, unreliable to get the data that you're looking for, and nothing is actionable. This leads into no clear business decisions on when to perform maintenance tasks, creating unnecessary silos where different teams are not working together to communicate this. Our solution that we proposed is a one-stop shop pane of glass that is layered with a predictive maintenance solution for monitoring offshore and onshore wind assets. By integrating the AVEVA Connect and advanced analytics tools into a clear digital solution, we can provide a clear and comprehensive view in real time. This holistic visualization enables our maintenance team and decision makers to see exactly what's happening at any given moment. AVEVA's solution creates a single source of truth where all stakeholders can access the same accurate and up-to-date information, all from the cloud.
We provided real-time access to Pi asset framework data streams such as wind speed data, active power, instrument status, and overall equipment effectiveness by configuring Connect data services to connect to Pi. Visualization services are used to monitor assets alongside an industrial AI assistant that provides contextual query responses by any persona. The data is also exposed to modeling and analytics facilities in AVEVA Advanced Analytics, the results of which are historized and pushed to the Pi data archive for consumption by the Pi asset framework, or simply visualized alongside existing data. To build a model appropriate for solving some of the problems the renewables industry faces, we talked with several engineers to gain insight into the best way to realize our solution. We conducted some investigation into turbine operation and maintenance and framed the use case around minimizing periods of downtime and power outage due to historical failures aligned with wind conditions. Turbine system failure rates were simulated and injected into the operational model of each turbine and the outputs used in predictive modeling.
The Asset Intellect tool is a way to bring different business systems together while also layering on top of an industrial historian. The screenshots here are a collection of the different parts of the system that we've built. We have a collection of different tabs that are all third-party tools that can be embedded into the solution, such as Power BI, ArcGIS map data for weather and wind conditions, event frame capture, and so forth. But more importantly, being able to integrate with tools such as the AVEVA suite of products, scaling a solution like this to dozens, if not hundreds, of other wind turbines becomes a much easier for the engineer developing this, but also brings the solution to the end user much quicker. The power of using a pane of glass tool is that not only the maintenance manager, but all different types of personas can bring together a collection of different business systems into a single source of truth and have their own unique landing pages, tasks, and operational insights they can see at a glance.
Having established a model in PyAsset Framework, the data is then exposed to AVEVA Connect Data Services. This service allows agents to be installed on PyServer nodes. The agents stream data for selected AF elements and implicit PyPoints, that is, PyPoint references configured in AF attributes. PyPoints can be added explicitly using tag naming parameters, and with a historical start time defined, the agent can begin streaming data to AVEVA Connect Data Services. The visualization services offered by AVEVA Connect can make all data processed by PyAgents available for consumption by visualizations of the standard variety and also types that take advantage of PyAF standard templates to contextualize equipment of the same type. Various dashboards have been created with the persona of maintenance manager in mind, ranging from raw inputs through calculated and derived outputs. The persona can then access data key to pursuing improvements in the operation and maintenance of their turbine farm by tracking turbines with lower than expected power output, efficiency, and with greater than expected repair time. Additionally, the AVEVA Industrial IAI Assistant is able to summarize operational conditions when prompted with targeted user-generated queries. This provides a crucial ability to drill down to issues presented by the data without the time-consuming task of interpreting which assets and equipment to prioritize. AVEVA Advanced Analytics allows sophisticated machine learning and predictive algorithms to discover trends in the data and predict future occurrences of failure and downtime as a consequence. The process is codeless, but requires a careful hand when designing the data flow, selecting the right analysis model, and training on the relevant data to produce a useful output. This service nonetheless saves an impressive amount of time and effort when it comes to manipulating data into datasets suitable for analytic consumption. With the AVEVA suite of tools building on the PyServer functionality, our persona, the maintenance manager, now can drill down to poorly performing assets, recognize common themes and failures, predict future failures, and set about structuring maintenance programs with greater effectiveness, increasing productivity, and saving on unnecessary capital expense. Data produced by the analytics service can be continuously fed back into a PyData archive using the reciprocal agent, the Connect to Py agent, to configure the data output for writing back to the Py historian. The last stage of the closed loop is to feed it back into Py to historize along with the operational data to fully integrate analytics into the holistic solution whereby future failure data can be used to rationalize and justify current operations.
So if you're wondering what's in it for the partners, yeah, the opportunity to showcase here at the AVEVA World Conference. The winner is the ITI Group Manufacturing Miracles. If you'd come up, please. All right. Steve, you can introduce your colleagues, and I'll let you go from there.
Sure. Thanks very much, Tim. And really appreciate all the help from yourself, the judges and the mentors that we had through the process. It's one thing that was missed out. We had some really good mentors hooked up to us from different parts of AVEVA, different specialities who were supporting us with supporting every team with the submissions that we were putting together. So we are Manufacturing Miracles. My name is Steve Taylor. I am a Principal Systems Engineer for ITI Group based out of the UK. We also have Roddy Manson and Cameron Brown, two of our data science engineers that have been working on this with me. And so together we have been Manufacturing Miracles. We have a customer. Our customer manufactures wet wipes in Western Europe. They have strong sustainability commitments. They are always seeking reductions in water, plastic, and energy usage. And in this case, our task that we took on was to optimize plant energy usage or to enable the customer to do that. Right now, they have quite vague emissions targets, and they have a need to try and establish what their Scope 2 emissions are, and to understand really what are the key drivers behind that at any given moment. And our solution was to help them attribute those Scope 2 emissions back to particular products, to predict the emissions based on live operating conditions, identify deviations from the prediction and likely causes, and empower the customer to drive down emissions. So, we had a very generous customer. They are a non-AVEVA customer, and they donated an MES database and historian data to us so we could have a play around with it and see what we could get out of it. And so the first challenge, the kind of first mammoth task, was kind of lifting all that data out of the existing SQL databases, transforming it, bringing through 4 years of data into 238 pi tags to help model the kind of critical aspects of the site that we needed for the solution. Second of all, for our initial submission, we built out some dashboards and initial metrics, trying to get a sense of what was going on at the plant level in a way that could give you some useful information around emissions. And then across the challenge this weekend, we've been building out more detailed metrics for the kind of CO2 allocation back to the line, and lifting that data up to connect and building on top of that using the latest tools. So in particular, applying machine learning in the advanced analytics platform to predict emissions and compare those predictions to the actual. So what's in a KPI? We had data from the lines. We know how many packs are being generated per minute at this kind of wet wipe manufacturing site. There were kind of 4 lines in our final solution. We had data for 7. Finding the right scope is always a challenge. We have the amount of energy usage being recorded by that line, and what we brought in was external third-party data telling us the emissions factor for this region at this time. So in AF, we were able to bring that data together to understand what are the Scope 2 emissions attributable to that line at that moment, and then, based on the number of packs, how much emissions per pack. So that's effectively the key metric that we brought together. And finally, in advanced analytics, being able to run regressions on that, to apply machine learning models to understand the kind of predicted value we would expect for that at any given moment. And this is where, when it comes to machine learning, you got to make sure, anything really, got to make sure you find the right solution for the right problem. I've seen plenty of people try to apply machine learning to problems where you already know the situation, you already know your variables, you've established the relationships between them, and you don't need machine learning to tell you something that you already know. And so the great thing about having this kind of CO2 attributable per pack is that it rolls in so many other key KPIs. It rolls in things like the energy usage, the current emissions factor on the grid at any given moment. It rolls in the efficiency of the line, any downtime incurred, and in all these things wrapped up, you get kind of one KPI that then has kind of complex underlying factors that you're able to regress on. So we chose, for our persona for the challenge, we chose Susie, the plant manager, who is interested not only in uptime, but in being able to optimize the attributable Scope 2 emissions for those lines at the time. So this is a little snapshot of part of a connected visualization services dashboard that we built, showing on the right-hand side the operation of the line. You can see periods of uptime and downtime there. And on the left, that's our calculated metric of how many CO2 grams per pack we are attributing back. Now, you might notice on the red line, 10:38 in the morning. Is it 10 or 12? 11:28 in the morning. You notice a spike on the red line. And so what are the key contributors behind this? Now, I need to caution this one because we actually we had a little bit of time to play with the industrial AI assistant during the challenge. As we were going through and experimenting with different prompts, we didn't have quite enough metadata in there to really usefully get answers to the questions that we were working with. So we got a lot of good information out around kind of generals in that domain, but without having more time to train it and bring together that metadata, we couldn't get a direct answer. So what we've got here is actually a mock-up based on information that we do know is there and available within the Connect platform. So we've asked the question, what contributors could have caused a CO2 spike on line 2 this morning? And so the first line is actually the direct line from the prompt that determined the CO2 spike, and it gave us a link where you could then get all the information for line 2 and the data on it, and then beginning to talk about different factors. So things that we do have is on the advanced analytics platform, we have already performed kind of complex regressions on the data. We know what the key factors are. We know that electricity usage, the emissions factor, and the production rate are the key drivers of this metric. That's the place to look to understand what's going on here. Additionally, there is information around the events that happened around this time on the line, with a leak test failure, hole tearing, various things around this moment that give you the next place to look in terms of the problem. So we had a lot of fun actually trying out the tools and building out the model here. For Roddy and Cameron, they are data science graduate apprentices. They study this stuff in university alongside their role with us at ITI Group. And on our initial submission, they were kind of working hard to try and get something workable in Python using the kind of standard libraries that they've been using in university. And we went through quite a few iterations trying to get kind of clear, provable value there. And then a couple of days ago, we got access to the Connect platform, brought our data into there. And the first thing I did was I opened it up and had a play around and tried to get something working, and it wasn't having an awful lot of success. And then I realized I'm not a data science specialist, but I have two. So I gave it over to Roddy and Cameron, and within 2 hours, Roddy actually had a really good prediction on the data variable we were trying to get. After having weeks of playing around in Python trying to get that same data. Initially, it was too good. We had to strip back some of the input variables to make sure that we actually were not over predicting, I guess, with the data that we had. But very quickly, we got to a really good, useful metric. So I was saying there how we know the effect of various factors. This is data available from within advanced analytics once you've done that regression to understand what are the key drivers here and how significant are they in terms of long-term variation, short-term variation, and general feature significance. And so here's the kind of the thread that Roddy set up on the data. Now, one of the cool things is that in advanced analytics, it gives you a load of pre-built models. We chose the energy optimized model, and we're able to go through kind of layer by layer and choose, which inputs, how exactly do we want it to handle this data in order to get the result that we are trying to establish. And I was actually really pleased with the results. So in blue, you have here the predicted value that the model was telling us in real time, and in green, the actual live values. So we continually streamed in historic data into into real time, effectively allowing us to do a real time prediction of data that the model had never seen before against the live data. So you see, generally, we've got a really strong correlation. So what can you notice here? First of all, we see there's a higher emissions per product during the day, during periods when the load on the network is higher, when you've got more kind of gas plants and things running, you've got higher CO2 attribution on the energy grid as a whole. So during kind of non-continuous production runs, by offsetting your production to low emissions period, you can actually reduce the emissions per pack. Second of all, there's a deviation that suddenly starts happening immediately following an ATM shift changeover. In the MES data, we can follow this back and see which team it was, what events were happening on the line, and gives you the next place to look at to understand the deviation that you have there. And the third thing here was that, great big spike and flat line there, and that was during a period of unscheduled operation when the line had just been left running. So for, I guess that's probably more than a day, is it? For more than 24 hours, the line had been left online when actually it really didn't need to be. And so again, just 3 opportunities for either kind of driving down the CO2 per pack or identifying opportunities for reducing that in the future. So there's loads of stuff I would have loved to have shown you if we had more time around all the technical aspects of it, but that is our submission. So at this point, we would like to invite you any questions from the audience.